Hello everyone, welcome to the new lecture of lecture series on network analysis and synthesis. I am Dheeraj Singh, working as an assistant professor in APS Engineering College. So, in the last class we have discussed about the RL and RC circuit analysis, how the RC and RL circuit response can be find out for step impulse and pulse response, as well as we have seen how we can find out the current and voltage after t equals to 0 after operating the switch. Now, in this class we will discuss about the RLC circuit, how the response of RLC circuit we can find out. So, these are the contents that we are going to cover today. First of all, we will see step response of series RLC circuit, how the RLC circuit will behave when a step input is applied to it, and how the parallel RLC circuit will behave when a step input is applied to it. Then we will do some questions on RLC circuit. So, first of all, what is step response of series RLC circuit? We have R, L and C connected in series, and we have to obtain its step response. So, first of all, we will write the equation as R into I of t plus L into di by dt, that is voltage across inductor, plus 1 upon C minus infinity to t I of t dt, and it will be equal to V of t. As we are evaluating step response, so V of t will be equal to V into U of t. So, V of t will be equal to V into U of t. Now, after taking its Laplace transform, we will obtain it as R into I of s plus L s into I of s minus I of 0 minus, this is the representation of di by dt, plus 1 upon C I of s by s plus q of 0 minus by s, and V of ut, u of t as a Laplace transform of 1 by s, so it will be V by s. So, I of 0 minus is the initial current through the inductor, and q of 0 plus is the initial charge across the capacitor. So, now we have replaced our RLC circuit, in which L is replaced by its series equivalent, in which it is represented by Ls and L of I of 0 minus in series, and the capacitor has been replaced with its capacitor 1 upon Cs and V of 0 by s. So, this is the circuit we have obtained in Laplace equivalent representation of the circuit for a series RLC circuit. So, here we are assuming 0 initial condition. So, because 0 initial conditions are assuming R of Is plus Ls Is plus 1 upon Cs Is will be equal to V by s. This is the equation we will be left with. Now, I of s will be equal to V by s. Now, on further solving it, it will be V by L square plus Rs plus 1 by C, and it can be written as V by L and 1 upon S square plus R by L into S plus 1 upon LC. So, now we are with the equation for I of s, and it can be written as V by L S plus P1 and S plus P2. Now, on factorizing or on finding the roots of the denominator of the equation, we can get two roots because of the second order equation, one is at minus P1 and one is at minus P2. So, P1 and P2 on solving the quadratic equation, we will get this one as minus R by 2L plus minus R by 2L square minus 1 by LC. These are the two roots that will obtain, which is obviously will be obtained by solving the quadratic equation in the denominator. And now, depending upon the value of the roots of this equation, we will have three possible solutions. So, first case, when both are real, when both will be real, for both to be real, R by L square, R by 2L whole square must be greater than 1 by LC, only then P1 and P2 will be real. So, in that case we can represent it as V by L by S plus P1 into S plus P2, On doing partial fraction, we can get it as A by S plus P1 plus B by S plus P2. So, A will be equal to S plus P1 into V by L. This is how we obtain the value of coefficients. We get it as A equals to V by L by P2 minus P1. Now, again the value of B S plus P2, V by L S plus P1 into S plus P2 at S equals to minus P2. So, here we will obtain the value of B as V by L into P1 minus P2. So, we have got the value of A and B in this equation. Now, I of S is A, which is V by L by P2 minus P1 into 1 upon S plus P1, plus B V by L by P1 minus P2 into 1 upon S plus P2. So, it can be written as V by L P1 minus P2 I have taken as common. So, 1 upon S plus P2 minus 1 upon S plus P1. Now, after taking its inverse Laplace, we will get it as constant V by L by P1 minus P2 e to the power minus P2 t minus e to the power minus P1 of minus P1 t. So, this is the current that we have obtained in case R by 2L square will be greater than LC, when we will have both distinct roots, get both roots as real and distinct. Now, second possible case is when the roots are real and equal. It may happen then that P1 will be equal to P2, and it will for P1 equal to P2, R by 2L square must be equal to 1 upon LC. Only then P1 will be equal to P2. We can write our equation I of S as V by L upon S plus P1 whole square, because both roots are equal. Now, we can obtain its inverse Laplace as V by L into T e to the power minus P1 t. So, this will be the current that will flow in case we have equal roots and both are real also. In the third case, which is possible, is when the roots are imaginary. So, when R by 2L square whole square will be less than 1 by LC, P1 and P2 will be complex conjugate. So, we will get P1 as a real part and complex part, and P2 also as real part and complex part, and both will be complex conjugate. So, the equation that we will have for the current is P1 is minus alpha plus j beta and P2 is minus alpha minus j beta. So, it can be combined and can be written as S plus alpha whole square plus beta square, and we will get it as V by L beta upon S plus alpha whole square plus beta square, and after taking its inverse Laplace, because of this value, we will get its inverse Laplace as sin of beta t, and S plus alpha it will be represented by e to the power minus alpha t, and the current will be V by L beta e to the power minus alpha t into sin of beta t. So, these are the three cases that we can have in our RLC circuit. Now, we will see step response of parallel RLC circuit. In this the switch RLC are connected in parallel. So, it's if we will assume 0 initial conditions, and because we are talking about step response, it will be equal to IDC by S, and C will be represented by 1 upon CS, R and L will be represented by L into S. So, when we will apply KCL in this equation, so it will be equal to V of S by Ls plus V of S by R plus V of S by 1 upon CS, and it will be equal to the current which we are providing as IDC by S. Now, on further solving it, we will get it as this one. So, V of S will be equal to IDC by S, S square plus 1 upon RC into S plus 1 upon LC, and IL of S, we know the current is V by Ls. So, IL of S is IDC by LC, and we get S square plus 1 upon RC into S plus 1 upon LC. So, this is the current, and again depending upon the roots we can have different cases for the circuit. And also we are going to discuss sinusoidal response of a parallel circuit. So, what will happen in the sinusoidal response? The DC value now will be represented by a sinusoidal input. So, I g equals to I m cos omega t. So, its Laplace will be I g equals to I m into s upon s square plus omega square. So, the value of voltage V of s I d c will be represented by now I g by c into s square plus 1 upon R c into s plus 1 upon L c. So, V of s is now I m upon s square plus omega square, the Laplace of the value of excitation sinusoidal input cos omega t I m upon s square, I m into s upon s square plus omega square. So, we will get it as I m by c s square. So, it will be s square plus 1 upon R c into s plus 1 upon L c. So, if we will substitute the value of I g in this equation, we will get it as I m by L c into s square plus omega square s square plus 1 upon R c into s plus 1 upon L c. Again we can find out the different cases for this equation to get the value of current I of t. Now, we will see how we can solve the circuit whenever we have, how we can find out the current or voltage in a RLC circuit. So, in this question we have to find out V naught. V naught is the voltage across capacitor for the circuit shown in figure, and we are not provided with any initial condition. So, I of 0 equals to 0 and V naught of 0 equals to 0. So, there is no current flowing in there was no current flowing in the inductor as well as no storage in capacitor. So, the voltage is 0 across the capacitor. So, when we will find out its equivalent, Z equivalent will be equal to Z1 plus Z2 plus Z3, because all are connected in series. So, Z1 is 6 and the current through the inductor value is 1 Henry. So, it will be S, which is SL, it will be S, and 1 upon Cs, and C is given as 1 by 8. So, we will get it as 8 by S. So, 6 S and 8 by S is the Laplace representation of RLC circuit, and we will solve it. We will get it as S square plus 6S plus 8. So, this will be the value of Z equivalent. Now, the output voltage we have to find out V naught S. So, output voltage V naught S will be equal to V of S. Here we are applying voltage divider rule. So, Z3 divided by Z1 plus Z2 plus Z3. Z3 we have a 8 by S. Z3 we have 8 by S. So, Z1 plus Z2 plus Z3 we have obtained as S square plus 6S plus 8 by S, and it will be equal to 1 upon 3 into S plus 3, 8 upon S square plus 6S plus 8. So, this is the equation that we obtain for output voltage V naught S. Now, on further factorizing it, we get the 3 roots as S plus 2, S plus 3 and S plus 4. Now, we will apply partial fraction. 1 upon S plus 2, S plus 3 and S plus 4 can be written as A by S plus 2 plus B by S plus 3 and plus C by S plus 4. So, A will be equal to S plus 2, S plus 2, S plus 3, S plus 4 at S equals to minus 2, get the value of A as half, and C will get the value as S plus 4, S plus 2, S plus 3, S plus 4 at S equals to minus 4, get the value as half. Again B can be find out and its value is minus 1. So, V naught of S will be equal to 4 by 3 by S plus 2, because 8 by 3 we have already, minus 8 by 3 by S plus 3 plus 4 by 3 by S plus 4, and after taking its inverse Laplace we will get it as 4 by 3 e to the power minus 2t minus 8 by 3 e to the power minus 3t, because of the root at S equals to minus 3, and the last one is root at S equals to minus 4. So, we will get it as 4 by 3 e to the power minus 4t. So, this is how we can obtain the value of A, B and C, and we will get the value of voltage across the capacitor V naught of t. Now, this is another question in again we have to find out the current I of t in a series RLC circuit. Now here we have to find out for two different input. First one is ramp voltage 6 R of t minus 1, this we have applied as an input, and in the second part we have applied step voltage which is 2 into u of t minus 2, and we are assuming that the circuit was initially relaxed. Because the circuit was initially relaxed, so the current through the inductor will be 0 and the voltage across the capacitor will be 0. So both current through the inductor and voltage across the capacitor will be 0. Now we can find out its Laplace equivalent. So its Laplace, in its Laplace equivalent, what we will get? We will get V of s, R will remain as it is because there are no initial condition. So L will be represented simply by S into L, and the capacitor will be represented by 1 upon C s, and this will be the value of I of s. So 6 into I s plus S into L is 1 I of s plus I of s by C s, C is 1 by 8, so 8 I s by s equals to 6 into, because the input is 6 R t minus 1, V of s will be equal to 6 e to the power minus s by s square, because V of t was 6 into R of t minus 1. We know the R of t has Laplace of 1 upon s square. So shifted in time domain by 1 unit will lead to multiplication of e to the power minus s in s domain. So after solving this, I of s is this one that we have obtained. Now we will do partial fraction. So we will get the, after doing partial fraction, we will obtain the value of a as 1 by 8. Then we will obtain the value of b as 1 by minus 4 or minus 1 by 4. We will obtain the value of c as 1 by 8. So now we are with the current equation 6 e to the power minus s, a by s, b by s plus 2 and c by s plus 4. So we are left with 3 by 4 e to the power minus s by s, 3 by 2 e to the power minus s by s plus 2 plus 3 by 4 e to the power minus s by s plus 4. Now when we will take its inverse Laplace transform, we will have 3 by 4 u of t minus 1, because of this e to the power minus s we will have t minus 1, then minus 3 by 2 e to the power minus 2 t minus 1 plus 3 by 4 e to the power minus 4 t minus 1. So this will be the current that we will obtain when we apply the ramp voltage. Then the second part, we have to we are provided with the input as 2 u of t minus 2. So the V of s now 2 e to the power minus 2 s by s. This will be the value of V of s in the equation. Now again we will obtain I of s and we will go for partial fraction. So this is the equation that we have with I of s. Again we will obtain a as 1 by 2 and b as minus 1 by 2. So I of s will be equal to 2 e to the power minus 2 s, half by s plus 2 minus half by s plus 4, and it can be written as e to the power minus 2 s by s plus 2 minus e to the power minus 2 s by s plus 4, and we will take its inverse Laplace. We will obtain with I of t as e to the power minus 2 into t minus 2 and e to the power minus e to the power minus 4 into t minus 2. So this is how we will obtain our current I of t. Now this is another question in which we are a switch is provided. The switch was closed before t equals to 0 and it gets opened at t equals to 0. So t equals to 0 माइनस से पहले स्विच क्लोज था और t equals to 0 के बाद स्विच को हमने at t equals to 0 पर हमने स्विच को क्लोज कर दिया. So at t equals to 0 minus switch was closed. So when the switch was closed, the capacitor will act as short circuit. So capacitor will act as open circuit and inductor will act as short circuit. So here it is open circuit and the inductor is short circuit here. So IL of 0 minus, which is the current, 6 by 2 plus 4, because no current will flow in this. So IL of 0 minus will be 6 by 2 plus 4, 1 ampere. The voltage across the resistor, will be equal to 4 into IL of 0 minus, and this voltage will be the same as the voltage across the capacitor. So Vc of 0 minus will be equal to 4 into IL of 0 minus. IL of 0 minus is 1 ampere. So 4 into 1, we will get it as 4 volt. Now IL of 0 minus equals to IL of 0 equals to IL of 0 plus, because inductor does not allow sudden change of current. So IL of 0 minus equals to IL of 0 plus as 1 ampere, and the voltage across the capacitor we have evaluated as 4 volt, which will remain as 4 volt even after the opening of switch. So at t equals to 0 plus, for t greater than equal to 0 plus, we have represented our capacitor with its Laplace equivalent. So in Laplace equivalent we have 1 upon Cs, and Vc of 0 by S is connected in series, and inductor, this is the Laplace equivalent of inductor, SL plus L into IL of 0 minus. So when we will write KVL equation for this circuit, now the switch is open, no connection with the source now, this switch is open now. So when we will apply KVL in this loop, so on applying KVL we will get it as 2SL into 2 into S into IL of S, and 2 volt, because the polarity is minus to plus, so we will get it as minus 2. Value of L into IL of 0 minus, IL of 0 minus we have obtained as, IL of 0 minus is 1 ampere and L is given as 2 Henry. So 2 into, so it will be 2 into 1, get it as 2 volt, plus 4 into IL of S, minus, because again we are going from minus to plus, so minus Vc of 0 minus S, plus 10 by S into IL of S, equals to 0. So we have applied KVL in this loop. So after applying KVL in this loop, we get the value of IL of S as 2S plus 4 by S divided by 2S square plus 4S plus 10 by S, or we can write it as S plus 2 by S square plus 2S plus 5. So S square plus 2S plus 5 can be written as S plus 1 whole square plus 2 square. We are writing in this form just to make the formula for cos or sine. So we will get it as S plus 1 whole square plus 2 square. So S plus 2 can be written as S plus 1 plus 1. So S plus 1 divided by S plus 1 whole square plus 2 square plus half into 2 upon S plus 1 whole square plus 2 square. And when we will take its inverse Laplace, we will get it as S plus 1 by S plus 1 whole square plus 2 square e to the power minus t, because S is now S plus 1 into cos of 2t, because we have S plus 1 in the numerator, that is why cos, plus half e to the power minus t into sine of 2t. So this will be e to the power minus t because of S plus 1 into sine of 2t into u of t. So this is the value of current through the inductor that we have obtained. So this is how we obtain the value of current as well as voltage in an RLC circuit. So this is the reference book that you can use to solve RLC circuit. Thank you so much.